Right then, so we're going to look at binary logic in this lesson. I'm going to split binary logic into 3 lessons. So this one will concentrate on why it's done as zeros and ones, and then we'll move on to logic diagrams, and then we'll move on to truth tables. Okay, so I'm hoping the pen's going to work much better this time. We'll put it full screen. So, reason we use binary. It's only used as zeros and ones. You do it in the binary table to do calculations, but you can also use them in logic gates and logic diagrams. If you remember rightly from, I think it's year 7 when you were taught this, if there is a 0, it just means there's no electrical current in the logic diagram. If there's a 1, it means there is electrical current. All right, it's all about turning circuits on and off. So we will go to next slide. Just to give you a bit of an example of how this might work. If you imagine a digital clock, in order to represent any number, it can use up to 7 of those blocks you can see on screen. If it turns certain ones on, it makes a number display on screen. Just to give you an example. So if you move your head back, you can see that is a large digital number 3. In order for that to turn on, the computer has had to turn on block number 1, 2, 3, 4, and 5. It has not turned on 7 or 6. So just to give you a clear look at the binary for that, this is not an 8-digit binary number. This is just 7 separate bits of binary. So you can see we've got an on for 1, 2, 3, 4, 5, and then we've got off and off. All you need to realize in this lesson is that a 0 would be off. A 1 is on. Okay? A 1 just means there is electricity present. And in order for this clock to display that number 3, it needs to power that, and that. Okay? It needs to power 1, 2, 3, 4, and 5. It does not need power going to 7 and 6. All right, so if you move your head back, you can clearly see there is a number 6 there. I want you to pause this. First of all, tell me which blocks are being used. So just write down which blocks are being used, which block is not being used. And obviously, can you do that in order in binary so that you've got the 7 bits showing up as to whether they are a 1 or a 0 to see which ones are turned on and off? Pause the video, do it now. Right then, so we will look at the answers. Boxes 1, 2, 3, 5, 6, 7 are switched on. Therefore, you've got 1, 2, 3 are 1s, 4 is a 0, 5, 6, and 7 are the rest of the 1s. Okay, so logic gates handle the 1s and 0s that come in. Okay, so if a logic gate sees a number 1 arrive on this side of a gate, all right, let's just put a magical gate in there. Okay, so this is to show the way that the electricity flows. So electricity will arrive at this end. Okay, it will arrive at this end here. It will flow through the gate, and then electricity will come out of the other side somewhere over here, or depending on which gate it is, it will not allow electricity to come out of this side. Excuse my diagrams, they are shocking. All right, I'm going to show you an example now, because what you need to remember is that the arithmetic and logic unit, which is in your von Neumann architecture, is one that we have covered, is what will handle these logic calculations. Okay, it looks at logic gates, it works out what needs to be done. These are gates. Okay, you may recognize them from year 9, you might not, it doesn't matter. Those are the, let's have a look, the 6 there. You need to know those ones. Okay, you need to know how to draw them, so you need this diagram here. All right, and you need to know their names. Okay, you just need to know these, and these by their name. You just need to know that other logic gates exist. All right, the ones you will have to draw are the top 3 that are circled, and you'll need to know their names. So can you make sure you've got them written down now, please? Pause this video and get it done. Right, so once you've drawn them, we're going to have a look at them. All right, so this is what's called a NOT gate. it will flow that way. So this is your entry point, and this is what will come out of the gate. So it does the opposite. So if there is no electricity arriving, so if a 0 arrives at it, a 1 will be allowed out. It will magically make electricity go out of this gate. Don't ask me how. I don't know that far in advance. If a 1 arrives at this end, so if a 1 arrives at point number A, so if there is electricity flowing down that circuit, it will not allow electricity to flow the other way. That's what your NOT gate does. Your AND gate is exactly what the name suggests. It's what I've written just there. It requires electricity to arrive at point A and point B in order for electricity to flow through this gate. Okay? So if a 1 arrives there and a 1 arrives there, a 1 will actually flow out of this gate. There are no other circumstances in which a number 1 will flow out the other end. The OR gate, okay, this one is exactly as it states, needs electricity at either A or at B, or you can have both as a number 1 and electricity will flow through, okay, and give you a 1 output. So it needs electricity arriving at one or the other, or to both, in order for it to flow through. Okay, so this is an example question that could come through. All right, it's very, very basic. This would only be a 1, maybe a 2 marker. Your first thing you do is you label the gate. We know that's an OR gate, and even if it does not ask you to label it, you label it anyway. So have I got electricity at that one, or both? Yes, I have. So Y would be a 1. Okay? That is basics of binary logic.